Alright, so we're going to do 3.2, logarithmic functions. Okay, so an exponential function has an inverse. Okay, and it's called the logarithmic function. Okay. So really logs help us to evaluate exponents, and these functions are just inverses of each other. So we're going to use those ideas of the inverse that we learned way back in 1.5 or 1.6 to kind of talk about some of this stuff. So an exponential function looks like y equals a to the x, and that's what we saw yesterday. Right? You have some base to an exponent. And a logarithmic function looks like y equals log base a of x. Which, if you were to change to exponential form, would look like a to the y equals x. So this is log form, and this is exponential. So, f of x equals log base a of x is a log function in base a. Okay, so this little a here is your base of your log function. And y is the exponent on base a needed to get x. Okay, so if you have log base a of x equals y, maybe last year your teacher said something like you could follow this path around and we draw this curvy line. Did your teacher show you that?
Yes.
Yeah, it's kind of an easy way to remember like what goes with what. So you start with a base. The log base becomes your exponential base. Logs help us find exponents. So that means that y becomes our exponent, and that is going to be equal to x. So this becomes a to the y equals x. Okay? So today we're really going to focus on how to kind of interchange these forms. So how do I go from exponential to log and vice versa? Okay? So let's do example 1 here. Translate from log form to exponential form. Okay, and let's say we started out with log base 2 of 8 equals 3. So right now it's in log form. I want to change it to exponential. In order to change it to exponential, you have to write it as the base to its exponent equals our x value. So you just follow this little path, right? So it becomes 2 cubed equals 8, which is a true statement, right? 2 cubed is indeed 8. You remember that from last year? Yeah, good. Okay. So now if you have log base 5 of 1 equals 0. Okay, let's change that one. Did you get 5 to the 0 equals 1? And we know that anything to the 0 power is 1. So you always want to, once you've changed it, you always want to double check to make sure it's true. Okay? How about log base a of b equals c. What would that look like in exponential form? Did you get a to the c equals b? Okay. And then let's just try one more. This will be d. Log base 16 of 4 equals 1/2. Do you have 16 to the 1/2 equals 4? And 16 to the 1/2 really just means the square root of 16, right? Square root of 16 is 4, so that makes sense. Yes?
Can we just write like square root of 16?
No, you need to show it as the base and its exponential power, okay? So it needs to take on this form of y equals a to the x. Okay, can I turn this? All right. So let's take a look at some more. This will be example 2. Solve for y without a calculator. Bless you. Okay, so let's start here. So let's say I had log of 100. Okay, and sometimes, but you know what? Let's change the directions. Let me change the directions so that you'll see what you'll see there on your quiz or test. So let's just say evaluate without a calculator. Okay. So when you have something like this, you can actually evaluate this by hand. And in order to do that, what you're going to do first is you're going to take this and you're going to set it equal, let's say, to y, okay, or x, or whatever variable you want to use, all right? So you're going to set it equal to a y value, and then you're going to change it to exponential form, because that is what we can work with, all right? So now, if you don't see a base, what is the base? 10, good. So if no base is shown, then it is base 10. And base 10 is just called the common base. Okay, so that means we really have a 10 right here as well. Okay? So now, in order to solve this or evaluate it without the calculator, what I'm going to do is I'm going to change it to exponential form. So I'm going to get 10 to the y equals 100. Based on that, what's y? 2. So y equals 2. Now, if you were to put this in your calculator, which I would like you to get out today because we are still going to be using them, type in log of 100. Did you get 2? Yeah, okay. All right, now let's say we had log of 10. Okay, so now I don't want to use my calculator to do this. I'm going to have to do this by hand. And to do that, again, I'm going to set this equal to y. If a base is not shown, I know that the base is 10. So I'll fill those two pieces in. And then I have to change it to exponential form. So I have 10 to the y equals 10. So therefore y equals 1. Okay, if you were to type in log of 10 into your calculator, you would get 1. Okay? You try this one. Log base 3 of 1 over 27. So we set this equal to y, right? We follow that around, changing it to exponential form. So 3 to the y equals 1 over 27. Now, we got to think about 1 over 27. What's 27? In terms of, can we get it to match a base of 3? Isn't it just 3 to the third power? So this is really like saying 3 to the y equals 1 over 3 cubed, but y is not 3. right? Because they're still not really the same base. How can I make these two sides match? Their bases match. Yep, bring it up, right? Flip it. So I get 3 to the y equals 3 to the negative 3. Because isn't 3 to the negative 3 1 over 27? Right? You flip it, you cube it, you get 1 over 27. So then that means that y equals negative 3. How many people got that one? Okay, so you have to think along those lines. How can I make their bases match? And I might have to do some flipping of the fraction. Okay, work with some negative exponents. Okay, how about, this is the last one here. So log base 6 of 6. So you set it equal to y. Change it to exponential form. You have 6 to the y equals 6. What does y have to be? 1. Okay, good. All right, so when we take the quiz and the test, because it is with a graphing calculator, I'm still going to expect you to show your work like this. So you're going to be able to check it, right, to make sure you did it correctly, but you're going to have to be able to justify your answer with work, okay, when I say to solve without the calculator. Sound good? Okay, so now let's continue. We're still going to talk about the same thing, but if the base is e, then it is a natural log, which we use ln. Okay, so that button is on your calculator. It's on the left-hand side, and it's just below the log button. ln stands for natural log, and it's just when you have log base e. Log base e is equal to natural log. We do not write log base e, we write natural log. It's the natural base. Just like when we have log base 10, we don't write log base 10, we just write log. Okay? All right, so we're going to do the same thing. We're going to solve without the calculator, but now we're going to do it with natural log. So let's say that I had the natural log of e squared. Now some of you will see this shortcut very easily. For me, I don't know what it is about natural log, but sometimes it makes me a little nervous and it kind of like trips me up. So what I always do is I change natural log to log base e because I understand it better that way. It's your choice, but we're still going to set this equal to y. Okay? And instead of natural log, I'm now going to have log base e, okay, of e squared equals this y. And now when I change it, I'll be able to match those bases. So you still change it to exponential form, so you still get e to the y equals e squared, so therefore y has to equal 2. Jake?
When you have the natural log of e squared, then from natural log, you just cancel out e.
They do. And it's because of this reason here. Okay, so it's actually a property, but it's because when you do change it to this exponential form, this is what happens. And so you can see that pattern. For me personally, I can never remember that, even though I've done this a million times. So for me, I have to write log base e. Okay, some people won't have to. All right. How about this one? The natural log of 1. Okay, try to solve that one by hand without the calculator, and then you can verify in the calculator if you'd like. So for me, I'm going to change this to log base e of 1 equals y, right? And then I'm going to follow that around. So I get e to the y equals 1. What does y have to be? 0, because anything to the 0 power gives us 1. So y equals 0. Okay, now put that in your calculator. Type in natural log of 1 and see if you get 0. Okay, verify in the calculator. You're going to have it, so you might as well use it to your advantage. Okay, moving on. Okay, we're going to keep doing some calculator work here. We're just going to evaluate in the calculator now with log and natural log. So this is example 3, and we'll just say evaluate with your calculator. So I want you to type these in and see what you come up with. Remember the log button's on the left-hand column, so is the natural log button. Did you get 1.556 for this first one? Okay, did you get 0.805 for the second? We're going to come back to the third. Did you get 2.097 for D? Okay, now let's talk about C. What'd you get? It's non-real, it's an error, right? It's a no solution. Okay, why? Anybody remember why? Anyone want to guess why?
Yeah, I think the inverse is negative.
So this negative is the issue, okay? And that is because the domain for log is from 0 to infinity. So the domain is 0 to infinity, all right? You can't take the log of negative numbers. It's like taking a square root of a negative. Just can't do it, all right? It's not within the domain. All right, so let's talk about some properties. These are also true for natural log because natural logs are just logs with base of e. Okay, so the first one is log base a of 1 will always give you 0. Okay, that's because if you change it to exponential form, a to the 0 equals 1, right? Anything to the 0 power is going to give you 1. So anytime you get log of 1 or natural log of 1, you know the answer will be 0. Okay? Number 2, log base a of a equals 1. And all of these logs you can replace with natural log. So that is because when you change it to exponential form, a to the first power has to be itself. Property 3 says log base a of a to the x will always give you x. So this is the one you pointed out, Jake, that when you have a log with a base and it has this same base here, when those two match, you can just always go right to the exponent. And if you think about changing this to exponential form, a to the x has to equal a to the x, doesn't it? Right? All right, property number 4. If log base a of x equals log base a of y, then x has to equal y, okay? This is called the one-to-one property. And this is going to come up a lot when we go to solve these. Okay, so the one-to-one property says that if these match, if the bases match, then x and y have to be equal to each other, okay? Everybody all right with that? Okay, turn the page. All right, we're going to look at a graph. So graph the following. Remember that exponential and logarithmic functions are inverses of each other. Okay, so going back in our minds all the way back to 1.6, which was a long time ago, okay? Remember all the properties that held true about inverses? You could interchange the x and the y, their points on the table would flip-flop, their domain and range would interchange, and we would see that reflection over the y equals x line. Remember all those properties? Okay, well, because these are inverses of each other, we should expect to see all of those things happening. So, I want to compare y equals 3 to the x compared to y equals log base 3 of x. Okay, so let's just think about y equals 3 to the x. We talked about this yesterday. Where is the y-intercept? At 0, 1, right? It also had a horizontal asymptote at y equals 0, didn't it? Right? Those were exponentials we talked about. What was the domain? Yep, negative infinity to infinity. And yes, this is always the case of an exponential. And then how about the range? It had to be 0 to infinity, where 0 couldn't be included, right? Because we had an asymptote there. And how about the x-intercepts? There are none, right? Because we had this horizontal asymptote. So in terms of an x-intercept, there are none. And this is true of just those parent functions, right? Like if we put some translations in here, things are going to change. But if it's just the basic function, these properties hold true. So when we go to think about the graph, okay, let's just make a little quick table here. If we have negative 1, 0, and 1, we know we're going to get 1/3, 0, and 3. Right, if I plug in negative 1, 0, 1. So negative 1, 1/3, I know that I have a horizontal asymptote here, and then 1, 3 is going to be like here. So here is my exponential function, y equals 3 to the x. Okay? Now, if these are inverses of each other, what is going to be true about all of the things going on here? Aren't they just going to kind of all interchange, right? They're all going to switch. So, in terms of a table, let's just start there.
It should be 0.
Oh yeah, 0 is not right. It should be 0, 1. Thank you very much. So in terms of the table here, aren't we just going to interchange all of these values, right? So we're going to get 1/3 and negative 1, 1 and 0, 3 and 1. Okay, and if we just think about, like, does this actually hold true? Will this check out? Let's plug some of them in and verify it. So if I have, like, let's say I have x is 3. So I have log base 3 of 3 equals y. In order to solve that, you have to change it to exponential form, right? So I get 3 to the y equals 3. Doesn't y have to equal 1? Okay, so that's where that point is coming from. If you wanted to verify the 1, you could have log base 3 of 1 equals y. When you change it, we know that 3 to the y has to equal 1, so therefore y has to equal 0. So you can check out that these points are all truly interchanging. Okay, we know that they are because they're inverses of each other. So now that I have that, I see that I have an x-intercept at 1, 0. I have 1/3 negative 1, and which is like here, and 3, 1, which is here. And so the graph of log looks like this. So I have y equals log base 3 of x. So let's talk about some more of those pieces that go with the log. Now, first of all, does everybody see that reflection happening here over the y equals x line? Right? That has to be true. If they're inverses of each other, they have to be able to reflect over that line. We can see that. Let's talk domain and range. So these are all the properties here. So what is the domain now of log? 0 to infinity. Well, doesn't that have to be true because the range of the exponential function, which is its inverse, was 0 to infinity, and those have to interchange. And what do you notice about the range? Isn't it negative infinity to infinity? Which is coming from this domain. We also see that we went from a y-intercept of 0, 1 to now this has an x-intercept of 1, 0. Why doesn't this have a y-intercept? Because now that horizontal asymptote at x or y equals 0 just became a vertical asymptote at x equals 0. It's pretty cool stuff, right? Okay, you guys just still don't think inverse is that cool. It's all right. One day you'll be sitting wherever you're going to be sitting 10 years from now and you'll be like, wow, that was cool. That's what happens in my dreams, at least. Okay. All right, last problem. All right, we got to talk about one more thing. Transformations. So let's just describe the transformation. So if we have y equals log base x plus 3, and let's do another one of y equals log of x plus 2 minus 5. Let's just think about what's happening there. So remember, anytime you look at these values that are being added or subtracted, you're always trying to ask yourself, is this value locked in with the x or can it be moved with the y? So what's happening with this one, with A? Up 3 units. Everyone agree with that? Okay. And B? Left 2 and down 5? I agree. Easy. Okay.